Carbon dioxide emissions are one of the serious problems of our times. Here at Econic Technologies, they're developing catalysts that could help turn carbon dioxide into useful polymers.
Econic's catalyst is essentially a catalyst that will allow you to use CO2 as a feedstock for making polymers or plastics. And the catalyst essentially works by reacting CO2 with a highly reactive hydrocarbon material on epoxide, but it lowers the activation barrier to this process to enable you to actually carry it out. In the absence of a catalyst, this reaction does nothing and CO2 can't be turned into a polymer. It's a homogeneous catalyst, which means it dissolves in the epoxide, which is a liquid, and it's made from an organic framework around two metal centers. We have a range of metals that are used for this, but mostly non-toxic metals such as magnesium or zinc we tend to focus on using. So on a molecular scale, the polymer is essentially an alternating polymer of a ring-opened epoxide, so that's two carbon units with an oxygen, and then an insertion of CO2. So you get an alternating structure of hydrocarbon with a carbonate linkage in completely alternating fashion.
So whilst generally you do studies using purified carbon dioxide from a cylinder, there'll be the added advantage if you could use carbon dioxide without having to go through these purification stages. And certainly if you're producing polyols on a chemical site, you generally have point sources of carbon dioxide available, which if you can then feed straight into that, you reduce a lot of your transport costs, your purification costs, and therefore make this whole system more efficient. At Econic, we've carried out a study using carbon dioxide supplied to us from a carbon capture and storage site and compared the results we've got from that with normal carbon dioxide from a cylinder to see what we get in terms of the polymer we've made. And in that particular case, we were using the epoxide cyclohexene oxide. We saw no difference between using pure carbon dioxide and the carbon dioxide that we were supplied from the carbon capture and storage. So the advantage that we've got with this, being able to use this form of carbon dioxide is instead of just capturing it and storing it long term, we've got a potential revenue stream for that carbon dioxide that's being captured.
So our technology enables the direct incorporation of carbon dioxide into a polymer chain, which means that the customers can replace a petrochemical feedstock that is very expensive with nearly free carbon dioxide. This allows you to replace and actually, avoid the production of up to 40% by weight of, energy-intensive petrochemicals. And it has been found by other research institutes that for every ton of carbon dioxide that you incorporate in that way into the polymer, you save a further 2 tons of carbon dioxide by avoided feedstock manufacture.
There's a large range of potential uses for these polymers. They have a lot of similarities in their properties to traditional polycarbonates, but the difference in structure means you can actually have quite a different range of properties in, for example, hardness or glass transition temperature, so temperature that it will melt at or it will change thermally. But in terms of applications, the initial market that we are looking at for these materials is in polyols for polyurethanes. And polyols are short chain polymers between 400 and about 10,000 molecular weight with hydroxy functionality on each end of the chain. And these are the essential building blocks of polyurethanes, which can go into anything from mattresses for beds, or foams for insulation foam inside your house, for example, or for foams for car seats, or they can be used in diverse things like elastomers that you would find in trainer soles, or as resistant coatings, for example in paints and things like that. So they can have a very broad range of properties.